So let's say that I had some function f of x that had the following equation. We'll let it be a quadratic with negative orientation. Just by looking at this, I can tell you that the graph of something like this would look something like, more or less something like that. And let's say that I pick a random point somewhere on this parabola. Let's say I pick this point right here. And the coordinates of that could be something like, let's say, -4, +2. So let's have a discussion about the derivative and what it does. So this is a function f of x, and this is what the graph of f of x looks like. How about the derivative, denoted f prime of x? I don't know if you guys have been shown the power rule or all the different shortcuts for a derivative. Maybe right now you guys are looking at the difference quotient using limits. Either way, I'll tell you right now that the derivative of this function is that. So this is the derivative of that. The derivative itself has a graph of its own, right? It has its own picture. And this graph would look, goodness, it looks something like that. But that doesn't really matter for now. Here's what I'm trying to say. What if you and I wanted to graph the tangent line that passes through this point here? And I'll just make it solid. A lot of times we make it dotted. I'll just make it solid here in blue. So I want to know the equation of that blue tangent line. Well, they call it a tangent line because it is a line. And recall from earlier years math classes that the equation of a line and point slope is something like y minus y1 equals m times x minus x1, where this point here, the point that it passes through, that's your x1, y1. Now, let me say this. All of this is anchored at x equals -4, right? This whole discussion that we're having for this particular example, it pivots on x equaling -4. Now, how exactly can I get the 2? If I take -4 and plug it into the original function, that is how I discover the y coordinate, which happens to be 2. And you know what? As a matter of fact, let me take this x1, y1, and let me drop it in here and here. So it's y minus 2 equals m times x plus 4 if you respect the double negative. Now, if you want the equation of the tangent line, all you need now is the slope. That's all I need. And the slope is sort of the rise over run of this blue line. But whose job is it to reveal slopes? Boom, the derivative. Just write this down here. This is our derivative. So all I need is the slope m. And that is precisely why the derivative was created, to find the slope of a tangent line at any location, which in this case is -4. So to finish this off, take -4 and plug it in for x, but here into the derivative. So let me plug in -4 there. That would say something like f prime and -4 equals -4 times -4 minus 12. And this is 16 minus that. So there's a lot of 4s in this problem. I did not mean for that to happen. There's 4s everywhere. So let me take that slope and drop it in here. And you know what? As I see this, I believe that the slope is possibly 4 because this is really steep and it's also positive. See that? The orientation is positive. So let me just distribute here real fast. Let me just distribute the 4 there, the slope. And I get 4x plus 18 because that's 16, but you add the 2 across. So if the goal, I didn't really write down directions, but if the goal was to find the equation of the tangent line, boom, that's the answer. So a couple of things. The derivative, you find it however you want. But what do you do with it? You tell the derivative your x location, and the derivative tells you the slope of the tangent line. And you take the same x coordinate, if you plug it into the original function, you get the y coordinate. Hey, what happens if you take the x coordinate and you plug it into the tangent line? Well, let's see, let's do this mentally. Take -4 and plug it in for x here. 4 times -4 is -16, plus 18 is 2, which is right there. And that makes perfect sense because the tangent line and the original function have one point of contact, this point here, which is called the point of tangency. So if you take -4 and plug it into the original function or into the tangent line, you of course get the same output or the y coordinate of your point of tangency. So the derivative has its own little deal going on. It has a graph of its own. The connection between the graph of the derivative and the graph of the original, we can discuss that later because there are some serious connections there. But for now, just know that if you plug in your x coordinate into the derivative, the number that you get represents the slope of the line that is tangent to the original at the point of tangency.